Hi, I'm Brian Mullen, and this is Balls Out Physics, episode 5.2, the conservation of momentum in space. Now, in the last episode, I looked at propulsion in a vacuum chamber, and the real reason I wanted to do that was to try and show how difficult it would be to construct a vacuum chamber that accurately resembles or accurately models an infinitely expanding outer space. And a lot of people offered to contribute to a GoFundMe account or donate to building one of these. And while I really appreciate it, there's already somebody out there who's working on one of these, and he's a guy named Rob Durham. You might be familiar with his work. If not, check out his channel. He actually sent me a message about his work on vacuum chambers, and he's done some propulsion tests with CO2 cartridges, and that's why I thanked Rob in the last episode and for that idea. And he's also looking at doing some experiments with radiation inside, or thermal radiation inside the vacuum chambers he's constructed. And he spent, it sounds like, a good amount of money on this, so there's already somebody out there doing it. If you want to donate to anybody, please try to get in contact with him. I asked him if he would mind if I promoted his stuff, and well, I wanted to get this episode out, so I didn't wait for a reply. Sorry, Rob, but I figured you wouldn't mind people donating money for all of your hard work. He's also working with an Australian engineer, but he and an Australian engineer are both working on this, and they're both engineers, which is really awesome to talk to other engineers about this stuff. There's a lot of people that are seeing the flaws in the model of our world and space travel and all kinds of things. So I wanted to get back into the action-reaction problem in space and also the conservation of momentum. One of the biggest, or the typical solution I kept getting for the action-reaction problem is you use the conservation of momentum to design a propulsion system. And I'll get into how that equation is derived in a second, but I also mentioned looking at the compressed gas as a spring, because maybe it's easier to visualize that way, kind of going over the example in episode 5 again, and then go into the conservation of momentum. So when you take a spring, this is the biggest spring I had, unfortunately, but when you take a spring and you push in on it, when you compress it, it pushes back on your fingers or whatever you're using to compress it with, right? Action, reaction, typical stuff. Now, to calculate the force in the spring, or the force required to compress a string, we use what's called Hooke's law, and that's what this is right here. The force to compress the spring is equal to negative k times x, and negative k is basically the stiffness of the spring, and it varies between different springs. And then x would be the distance required or the distance of compression that you apply. So if I compress it this much, there would be that much force in it, depending on what that distance was that I compressed it. And then you compress it more, there's more force, and then more and more force. Does that make sense? And that's the reason it's negative, because it's the amount of force required to compress the string. And then whatever force that is pushes back on both of my fingers with that force, that reaction. Okay, so the reaction on each one of my fingers is equal to Fs. Okay, pretty simple. And so somebody suggested on episode 5 or used a spring. We were talking about the spring and how that could explain the compressed gas in a container that was sprayed out into space. That's what I talked about in episode 5, and how that could possibly explain the reaction. And so I thought that was a really good analogy and a good way to simplify it and look at it. So what I did was I drew the container here with a spring, a compressed spring in it, instead of the gas. The spring is basically taking the place of the gas, to simplify it. And so what I've also set up here are 3 time intervals, okay? And the spring has been compressed right here to over a certain distance x, which I've got down here. Okay, so this is actually time equals 0. And we're going to say the shuttle is on this side of the container, and then space is on this side of the container. Okay, this is the same container at 3 different time intervals. Okay, so 1, 2, 3. It's the same thing. So what happens is we compress this string, or the spring, and get a force, Fs. And so, as I showed with my fingers, Fs at time equals 0, or time interval 0, Fs is equal to Rho, okay? That force in the spring is pushing on both the shuttle, or the backside in the container, and this side over here, which would be the nozzle for the compressed gas, or the door in this case, like a container, or the door of the container. Okay, and so Rho is pushing on both surfaces. And so, simulating the compressed gas, the lid flings open. And that's what we have here. And we assume that it opens so fast that it doesn't hinder the spring expanding at all. The spring just immediately starts to expand, just like the gas would expand out into space. And since it's springing out into space, there's no resistance at all. Now, on Earth, there would be a little bit of air resistance, but it would be pretty much negligible because it is a spring. But the best place to test this would be in a vacuum chamber. However, I don't think the air pressure would make that much of a difference. But so the door flings open, and here at time interval 1, that doesn't mean 1 second, whatever that would be fractions of a second, because this thing's going to spring out very quickly. So whatever that time interval is not really important. At time interval 1, door swings open, and now you have a different reaction on the shuttle right here. But that reaction is less than your original reaction, because if you think about it, if I just move my thumb, I just move one side, the door would be, my thumb would be the door. As the door opens, immediately after the door opens, the load on my index finger becomes less, right? It makes sense. Compress a string, you can do this if you have a spring. So at time equals 1, the moment that this door flies open, R1, the reaction on the shuttle starts to decrease instantly. So R1 is less than Rho, okay? And so now I drew this orange because the spring, the red represents the most compressed state. Now orange, the spring is relieved a little bit, and it's starting to come out of the container at time interval 1. Okay? Now we move down to time interval 2, and this is when the spring has now become completely relieved. It's like this. It's completely relieved now. Okay, and it's just about to fly out into space, because as you would expect, it would fly out into space. And so, right here, R2 is actually 0. R2 equals 0, less than R1. Okay, so throughout this entire process, this reaction on the shuttle that has this container mounted in it never increases, ever. It always decreases once this opens. And so this is to try to simplify the compressed gas. Now the compressed gas would be different because it is different because it's pushing on the back, but it's also pushing on all sides of the container. However, once you open one side, once you open the nozzle, all of the gas rushes out into space and doesn't see any resistance because space doesn't push back. So there's no reaction from space. So even though it's pushing on all three surfaces, as well as the nozzle or the door, once there's an exit into emptiness, into infinite expansion, all of the reactions on the container start to decrease. There's never a net increase of reaction on the shuttle, so it can't push the shuttle, it can't move it. And that's what I was trying to explain in episode 5. And so that's the basic idea of how it works, just simplified in a spring, and also gives you a good idea of how springs work. Okay, so if you've got a spring, mess around with this and see, hold it down, maybe launch it up in the air, and think about does that reaction increase? You can push it down on a table and launch it fly up. Does the reaction increase once you let go of the spring, like the load being pushed down on the table? Because remember, action, reaction, just everything we do is basically action, reaction. Okay, so that's the idea explained as a spring, and then of course in episode 5, a few people commented that the conservation of momentum explains this. Now I want to look at another example to do this, to talk about the conservation of momentum, but I figured we should break it down first. So let's go ahead and erase this. Now that that's all been covered, I need to get my whiteboard a little more secured. Now, the conservation of momentum, how is that actually derived? Where does that come from? It's an equation, right? And this is what is used to design these propulsion systems, basically. Well, it comes from Newton's third law, action and reaction. Newton's third law says F1 is equal to negative F2. Okay? Force 1 is equal to the opposite, equal and opposite reaction, F2. As I crouch and push it down on my feet, the floor pushes back with negative F2, or however you want to look at it, okay? Well, now, if you remember from episode 2, force is equal to mass times acceleration, ma, okay? So we can rewrite this as m1 a1 equals m2 a2, okay? And now, if you remember, I think I covered this in episode 3, that acceleration is equal to the change in velocity divided by time, okay? So again, we can rewrite this as m1 equal m1 times delta v1 over t equals m2 times delta v2, actually equals negative, stays negative, over t, okay? So m1 times the change in velocity of this mass divided by time equals negative m2 times the change in velocity of m2 divided by time. And time is constant, it's not different for each mass. The whole thing occurs over a set time. So multiply each side by t, since it's the same, it's constant. T cancels, and you get m1 times delta v1 equals negative m2 times delta v2. This is the conservation of momentum equation. It is action and reaction. It is Newton's third law. It's the same thing, it's just a different way to write it. Okay? And on episode 5.1, somebody suggested a fire hose. A fire hose is explained with this equation, how when a firefighter turns the fire hose on, it pushes back on them. I mean, they can push back pretty hard, and sometimes it takes a couple of guys to hold a fire hose. And I had to think about that one for a bit, but I want to do an example looking at a fire hose and how this equation can be used to figure out what velocity the fire hose would experience if there was nobody holding it or nobody there to get the reaction, and then compare that to what would happen in space. Okay, so I'm going to draw another sketch and I'll be right back. Okay, so here we go. What I have drawn here is a fire hose. Here's the hose, here's the nozzle. Okay, up here I have the equation. What I did was I said the reaction from the force of the water on the hose, the reaction acts to the right and the force of the water acts to the left. And what I'm saying is your right is positive, your left is negative. Okay? If you're watching the video. And so reaction, action, and then that can be converted into the conservation of momentum, as I just showed. And so what we have is water's flowing through this hose to a nozzle. And this nozzle works just like the jet engine, or very similar to the jet engine I showed in episode 5.0. And so you have water flowing through this hose, through the fire hose, and it gets to this nozzle. And as you can see, the shape reduces the area of flow, so the energy of the water increases, and that's what this red line represents, is the increase in energy, which is results in an increase in velocity as the water comes out of the end of the hose, okay? And so what I have here is VWI for the initial velocity of the water before it goes through the nozzle, and over here I have VWF for the final velocity of the water after it comes as it comes out of the nozzle, all right? Okay, so hose, the initial, I've got also here the initial velocity of the hose, right? So VHI is equal to 0 because the hose is just sitting there, it's at rest. And we're going to assume that nothing resists the hose's movement when the water kicks on, because obviously the hose is going to fly backwards, right? Unless there's firefighters to hold it. So, breaking down the conservation of momentum equation, we can solve for what we'll call VHF, what the final velocity of the hose will be after from the action reaction of the water, the action of the water, the jet of water pushing back on the hose, and then this is the reaction here. And then since there's nothing to stop it, since nothing's resisting this reaction, it'll move. Okay, that's the idea. So what we have here is the equation I wrote out before, and we can expand. It's delta V is, or your change in velocity, is your final velocity minus your initial velocity. Okay, so m hose, mass of the hose, times VHF, okay, no, I wrote that wrong, VHF minus 0, because we have VH and the initial velocity of the hose is 0, is equal to negative mW, mass of the water coming out of the hose, is equal to VWF minus VWI, okay? VF, VI, water. So now very easily we can solve for the velocity of the hose as it travels backwards. VHF is equal to get MH on the other side, just divide both sides by MH, it cancels here, and that gives you negative mass of water times VWF minus VWI divided by MH. That's it. That'll give you this velocity, and as you see, it's negative, so it's back this and it forces the hose back in this direction. Pretty simple, right? This is basically how these propulsion systems would be designed using the conservation of momentum in space. But as I showed in episode 5 with the jet, there's always an action and reaction. You have to count. The action and reactions continue. So there's consecutive action and reactions happening here. We have to count for all the action and reactions. And so when this water sprays out of the hose, immediately the air is resisting it. Okay, remember P atmosphere, P ATM, we'll just call it atmosphere for now, is equals 14.7 psi, assuming that this is at sea level. So as this water, this accelerated water, the increase in velocity comes flying out of the nozzle, the air is trying to resist it, but obviously there's so much energy here that the air can't resist the end of the stream. But just like in the jet engine, it is pushing down from above and below, and that's what creates this stream here. That's what holds it in a water jet coming out of the end of the hose, is this pressure. Okay, and so eventually the air will slow the water down, and you do have the weight of the water pulling it down, so you'll get more of a shape like this. If it doesn't spray infinitely, eventually the weight pulls it down, and the air pressure does slow it down. But that is what creates that jet effect, and it is the air pushing back on the water that continues the action and reaction process. So now here, see this, you basically have our water equals negative F air in a nutshell. But this sends like a ripple through the air, and it's like dominoes of air being pushed backwards until the air finally resists it. And it happens instantaneously when you turn the hose on, and that's why you get kicked backwards. I mean, you just can't see it because it's air. But this is what happens. There has to be consecutive actions and reactions. Every action has an equal and opposite reaction. Newton's third law, I believe it's true. It's everyday life. We know this. We experience it all the time when we're walking around, picking up a toothbrush, brushing your teeth. Every single thing we do has an action and reaction. If it didn't, we couldn't move. We could not control our movement. Okay? So, pretty simple. So, let's now consider this in space. All right? In space, say this is, instead of a hose, instead of a fire hose, say this is one of the jets on the shuttle. Okay? And that's the nozzle of the jet, or this would be propellant. Okay, so this would be P, and this would be VS for shuttle, and the reaction of the shuttle is equal to the force of the propellant. And see where I'm going with this, shuttle, propellant. Okay. And then shuttle, propellant. Well, remember, this is action-reaction. It is. So, if the designer, the engineer, is only looking at this and ignoring what's happening out here, he or she is assuming that there is a reaction happening out here. And I think this is how we have all been duped. I do. I believe this. It's taken a while to come to this, but when you really think about it, if you don't think about it, you're automatically assuming that action-reaction is happening out here. But in reality, if this is infinitely expanding space from the edge of the nozzle in the jet in the shuttle, then if this expands infinitely in all directions, and there's nothing pushing back because space is pulling away right at the edge of the nozzle, space is infinitely, there's a pressure differential there, negative pressure, whatever you want to call it, it sucks, whatever. There's nothing pushing back. So, in reality, VSF would be 0. Because you didn't sort of satisfy this, because the conservation of momentum is this equation. If there's no reaction between the propulsion, the VP, the propellant, whatever, then you don't have consecutive reactions back to the nozzle and you can't move. It's that simple. And that's what I believe is my opinion, but it's logical to me. And being an engineer, going to school and just knowing how engineering is, we go to school, we do complex problems throughout our college career, and we're always doing complex problems, looking for complex answers, and we constantly train our minds to look for complex answers. And so it becomes very easy for engineers to actually miss simple explanations. I see it all the time, but nowhere have I seen it more than in myself. I've had a problem, I've over-analyzed it, and I've asked another engineer, and they go, duh, and they point at something, and I'm just like, oh. Or just give me a simple answer, and I'm like, oh. And I've done it to other engineers. It happens all the time. We live in a very complicated society, and it does not surprise me when I really think about it that this could happen. So, you think it could be one massive conspiracy? Well, really, if engineers are designing these propellant systems for spacecraft and satellites and all these things, and they see video of them, they think it works. They forget about this action-reaction that's not happening because they only stick to this part right here. And if you just stick to this, you will get a velocity. If you do this calculation like I just did and ignore what's going on out here, okay, just like I did before, now we're saying mass shuttle equals VF or VSF minus V SI if it's moving, or we can assume it's not, and that equals negative mass propellant times velocity propellant final minus velocity propellant initial. And they can solve for this, and they can say, you can divide both sides by ms, okay? And so that gives you VSF minus VSI equals negative MP times VPF minus VPI over MS. And then you can just add VSI to both sides, and then you have velocity shuttle final equals negative MP propellant times VPF minus VPI over mass shuttle. Sorry, I'm going through all this. VSI. But then you can use this equation for other things. You can solve for the mass of the propellant you would need to create the velocity you want. All kinds of things. You can rewrite this equation, and as long as you're just ignoring that there's no reaction over here, you're assuming that there is a reaction, and so you're going to get values, and you're going to get numbers, and it's going to appear like it works. But if all this footage we've seen from space, which there's tons of hoax videos out there, and when you consider everything I talked about in episode 4 and all the work that everyone else out there in the truth community is doing, it doesn't add up. And this doesn't add up because there's no reaction happening out here. So it wouldn't actually work when you really think about it. So that just kind of gives more credit, more validation to these videos that show all the anomalies of ISS footage and moon landing and all that stuff. So this is how I think it happened, and this is how I think a lot of people who work for these space agencies have been duped, and they don't realize it. And it's very unfortunate. But I think we have to swallow our pride and just deal with it. So, where do we go? We've been, for the past 50 years, give or take, we've been, in my opinion, kind of living in a world of confusion. Our eyes see these things in space, and we're told about satellites and all these things, but I think our hearts are saying, no, that doesn't make sense, because this action-reaction is common sense. We know this. One of the things I loved about high school physics was I realized that it was kind of common sense, and we were just applying values and names and numbers to things. And I loved physics when I was in high school because of that. So, yeah, I think this is what has happened, and thanks for everyone for all the great comments, and even the critics out there. This kind of helped me get to this, and I think this makes sense, but it's up to you to decide what is true, because when it comes down to it, there's really only one person in this world who decides what's true, and that's you. You decide. You let your mind look at things, and in my opinion, let your heart decide if those things are true or not, because I think that's how we work, and I will get into that in later episodes now. That's also your decision as well to think about how we work, but I do think that's how we work. And so I don't think space travel is possible because of this, at least using propellants. Now, if we use bullets, again, the bullet, going back to episode 5.0, you have two masses with an action happening between them and blowing them apart, and that would work. If you had barrels sticking out of some type of spacecraft, I think you could move that way. It makes a lot of sense. And the same goes with the skateboard example. There's two masses, myself and the skateboard and the cinder block or the CMU block, and my arms are the action throwing it away from me. It would satisfy this equation, action, reaction. It would all work. You could solve for the velocities and go from there. So, that's it. I'm going to get into some different stuff in episode 6, and maybe I can go over the bullets again if I need to in another sub-episode of this, if people tell me this doesn't make sense. But like I said, decide for yourself. I'm not telling you what's true. I'm just telling you what I know is true now, after lots of thought and lots of research. It's just, like, there's never been a human being in space, and there's never been a satellite or anything in space. And what I feel really bad for is that dog Laika that the Soviets launched. Dog had no idea what was about to happen to her. At least humans know what they're getting themselves into. So, yeah. I will get into a lot more stuff. I'm really enjoying working with everybody in the truth community. It's a beautiful group of people. And so this time I'm going to leave you with a quote following this presentation from who I think was the greatest engineer who ever lived, and has been forgotten, but people are starting to remember who he is. And so I'll leave you with that after this. Until next time, peace.